Yeah, comes on everyone. Let's start off. Did anyone got this answer? Did you try? Forgot there is a homework problem. That's why I gave you 5 minutes to try. 2 mu mg by k, 2 mu mg by 3k. God, I said they're pulled apart by a. तो आंसर a का टर्म्स में आना चाहिए. You created a new answer of your own. मैं फ्रिक्शन म्यू दिया ही नहीं कहीं पे भी. Where did I give mu in the question? You guys na can be good fictional writers. Right? You can create stuff out of nowhere and write, books. Let's see. So 46 m by 15k. Others do keep your cams on. Abhinav, Taksha, Devansh, Soham, Ojas, cams on. Let's see how do we do this. First thing, let's start with an FBD. Let's say you pull them apart and let the elongation be x. So let's say this thing moves x1. Let's say this thing moves x2. X is equal to x1 plus x2. So both will not move the same distance. Let this be acceleration a2. Let this be acceleration a1. Let this be friction F1. Let this be the spring force Kx. This spring force is Kx, and this is F2. This is alpha 2, and this is alpha 1. Clear with the FBD? Any other horizontal forces? Vertically, N and mg is there. I'm not writing it. Yeah, now it is not slipping. So if it is not slipping, still our pretty nice point is there. This point of contact. I'll just call it A and B. So if I take torque about A, that guy will be Kx into R is equal to minus Ia alpha parallaxes theorem. Ia will be 2 by 3 mr square plus mr square. So that's 5 by 3 mr square. I'm skipping steps. Ask me if you're confused. And we also know it is not slipping. So A is equal to A1 is R alpha 1 here. So this thing will end up to be A1 is equal to minus 3. Remember, this is Kx minus 3Kx by 5m. Got this? Now be careful, don't say this is omega square. Why? When you pushed it by x1, you got acceleration a1. So a1 is equal to omega square into x1. ये होना चाहिए ना equation. Are you getting the catch? When you displace a body by x, then the acceleration is proportional to that x. The hollow sphere has moved x1 and the acceleration is a1. So a1 must be proportional to x1 and that would have been omega square. Is that making sense? So don't say this is omega square. That's a blunder. Hope that is clear. So what we are trying to get is, we want a1 is equal to minus omega square x1 or a2 is minus omega square x2. That's what we want to get. Fair enough. Then that might be right. Let's see. For this guy, when you take torque about B, again, we have Kx into R is equal to IB. It's a solid sphere, 2 by 5 mr square plus mr square, parallaxes theorem. 7 by 5 mr square alpha 2. Here also it is not slipping, so A2 is equal to R alpha 2. So we get A2 is equal to minus 5Kx by 7m. This is 1 and this is 2. And from here we can clearly see the relation. If I divide A1 by A2, I get 3 by 5 and 5 by 7, which is 21 by 25. And this is also equal to x1 by x2, na? Because A is proportional to x1, A1 and A2 is proportional to x2. So I got x1 and x2 ka relation. Is this making sense, everyone? Once we got this relation, that means x1 is nothing but 21 by 21 plus 25 into x, because x1 plus x2 is x. So x1 is nothing but 21 by 46 into x. So take this thing and put it in equation 1 or equation 2. I can put it in equation 1. So I know a1 is equal to minus 3kx by 5m, and we know x1 is equal to 21 by 46x. So take this guy x and dump it here. We get a1 is equal to minus 3k by 5m into 46 by 21 into x1. There. Now this guy will be 46k, and that will be 35m omega square x1. So that is your omega square. So time period is 2 by root over 35m by 46k. And what about the amplitude? We got x1 is this ratio, so a1 must be 21 by 46a. a2 will be 25 by 46a, because the amplitude also will divide in the same ratio as x1 is to x2. Main thing is here, check it out. Meaning, if you see, right, it looked dangerous, but we just simply took two torque equations and then we said the most common mistake what people do, right? They take a1 is proportional to x, they think this is omega square. That is a mistake generally happens, so be careful with that. If you displace by x1, then a should be proportional to that x1. Here, x is the total elongation in the spring. A1 doesn't know who is x. I hope you're getting this. Any doubts on this, please ask me. Any doubts on this page? This is just solving, so. But got the main theme, right? You have to start with an FBD. There's no other way out. Let's see one more. We'll do sphere one only, and then we'll go to that. So we got a solid sphere. We have a spring connected to the top. We have a spring here. We have a spring here. Total 3 springs are there. K1, K2, K3. K2 is at the center. K1 is at the top. This guy is R by 2 from the bottom. Mass is M and radius R. No slipping. Find time period for small oscillations. Think. I'll give you 2 minutes, then I'll explain you a bit, and then I'll give you a minute. Remember the story. Displaced by X, find the restoring force, find the restoring torque in proportional to this. Story is all the same. Let's see. So let me ask you a question. When I displace this cylinder by X, do you think all the springs will displace by X? That is a question you need to ask yourself. Let me help you with this. Suppose if you have a sphere and if it is rolling on a floor, what is the velocity of the point on the ground if it is not slipping? What is the velocity of the point at that instant? Zero. If the velocity of the center is v, then what is the velocity of the topmost point? V plus r omega, which is 2v. Then what will be the velocity of this point here? This will be v minus r omega by 2. That means v by 2. So what does it mean? If the center moves by x, the topmost point will move by 2x. The bottom, this center point will move by x by 2. Is that making sense? So every spring will not compress or elongate by same amount. If you move the center of the sphere by x, the upper spring will compress by 2x and this lower spring will compress by x by 2 and the center spring will stretch by x. Is that making sense, everyone? You can do this because the oscillations are small, or else the spring will bend and this point will come here. We don't want to get into that one. Is this clear? I hope. That comes from no slipping condition. Now try. So we start with that problem. Assume the sphere is pushed by x to the right. Then find the elongations and compressions in the spring. Then write the forces. Then take torque over the bottommost point. Question is over. The mistake is this: people don't realize that the each spring is elongating differently. If you got that question, I think that's the main thing in the what. Anyone not convinced with that thing, please ask me. K3 will come in the answer. Let's see. Answer won't be that great. So if you displace this by x, the spring is pushing you with k1 into 2x. The spring is pulling you with k1 into x. This guy is also pushing you with this k2 into x. This is k3 into x by 2. Let this be acceleration. Let this be alpha. We will take torque about the bottommost point because it's not slipping. Then you're done actually. Torque about A will be k3 x by 2 into r by 2 k2 into xr plus k1 into 2x into 2r. This is nothing but minus ia alpha. This will be k3 by 4 rx k2 xr 4 k1 xr. Ia will be, it's a solid sphere. So 2 by 5 mr square plus mr square minus 7 by 5 mr square alpha. And A is equal to R alpha. One R will cancel. You will get A is equal to minus 5 by 7m. 4k1 plus k2 plus k3 by 4 into x. That's your omega square. You'll get the time period from here. Make sense? Any doubts on this? So the main thing was that each spring will have a different elongation. Any doubts on the steps? If they ask you to find a friction, what will you do? Actually, भूल गया मैंने. एक और force होगा. There'll be friction also. How will you find friction? F minus this minus this minus this is equal to m into a na. And a ka value to I know. Substitute there, you will get f ka value. Makes sense. So I didn't ask you that, but if they ask you find the friction value, f minus k1 2x minus k2x minus k3x by 2 is equal to mass into acceleration. So take this and dump here, you'll get f ka value. Got it. So from there, they can ask you find the maximum amplitude. So all those kind of questions can be framed. Next one. Clear na? Daksha, Devansh, Ansh, Ahna, Arnav, Arush, Sharman, Surya. Surya, adjust your camera a bit. Can't see you clearly. Next one. We have a plank here. Mass M. You're resting on a cylinder on a floor. There is no slipping at any surface. This is connected to a spring. You're getting how it is? So you have a drum there, cylindrical drum, solid one. On top of it, you kept a plank of mass M. So there's no slipping between the plank and the cylinder. There's no slipping between the cylinder and the ground. Spring K is there. Find time period for small oscillations. How do we proceed? Try. I'll give 2-3 minutes. Hmm, 27 by 20, 11 by 8, 4K by 11. Yeah, three different answers. Let's see. Same thing. So let's say this thing is pushed by X. If the cylinder moves by X, how much will the plank go? 2X. I hope you have taken that into account. Because the plank is sitting on the topmost point, and if it is not slipping, it should have the same displacement as the topmost point. Now, if you write the forces, that means if this guy is going with acceleration A, the plank will go with acceleration 2A. So acceleration of the plank is 2A. This forces will be spring force K into 2X. Here we'll have a friction F1. That same friction will act F1 on this cylinder. There'll be one more friction here, F2. Check this out. Angular acceleration alpha. This is the FBD, everyone. Check your FBD. Once you got this, now for the plank, so there are two different frictions actually. One friction between the plank and the cylinder and one between the plank and the ground. This will be F1 minus 2kx is equal to mass into acceleration of the plank, which is m into 2a. So we have one equation here, F1 is 2kx plus 2ma. Next thing, we will take our favorite point, the ground, torque about A. F2 ka torque is gone, we have only F1 ka torque, so that is F1 into 2r is equal to minus Ia alpha. But what is F1? That is 2kx plus 2ma into 2r, and this is a solid cylinder, so it is mr square by 2 plus mr square by mr square, so 3mr square by 2 alpha. Looks like we are getting 8 here. 8, no, wait, there is ma also on that side. This guy will be 8kx plus 8ma. 1 r will cancel, that will be 3ma. 11ma is equal to minus 8kx. You're right, Falak. Please check others where it went wrong. Are the steps clear, everyone? Yeah, see, the same thing. Like, I am just doing the same thing. You draw an FBD, but when you draw an FBD, you have to be clear what is the relation between the accelerations, what is the elongation. So those are things you have to be careful. Most people, right, they goof up the acceleration of the plank or they goof up the elongation in the spring. So these are the things you have to be careful. Once you got this, you can find F1, F2, everything can be found out. You can take this A and put it here, you'll get F1. If you got F1, then I can get F2 also. F2 minus F1 is MA. So I can calculate F1 and F2 also. Clear, everyone? Any doubts on this? Nikhil, Soham, clear with this? Adi, clear? Arya, Parth, Kishana, got it? Next one. We have a rod here connected to a spring. Okay, this length is L by 2. Rod is mass M and length L. And here we have a block here. This is connected to a block of mass M. Gravity is there. Initially, system is at rest. You can make this more deadly by putting a container and putting some water also. You can bring buoyant force also into the picture. You can do that, but let it be. For now, I'll be a good person for today. So then find time period for small oscillations. This could be a good more than one choice question. Find time period for small oscillations and find the value of M for the system to oscillate, or find the condition so that there is an SHM. So they can ask you things like that. You will see once you get the time period, you'll realize there is a chance that system will not oscillate. Oscillations. Let's get this. How do we start? Start like this. Let this rod be displaced by small theta. This will be alpha. Start from there. So you need to get alpha in terms of this theta. मेरे आंसर अच्छा आंसर नहीं आएगा. Think. Draw an FBD. If you displace this by theta, will the block be at rest? What will be the elongation in the spring? See, it is all about asking questions. Most people think you're solving. No, you need to ask your questions. Okay, what is this happening? What is that is happening? Initially, when it is vertically, what is the torque due to mg? Zero, right? It is passing through the hinge. But if you displace by theta, mg ka torque will come. That means the torque due to mg is changing. We have to include now. Till now we used to ignore saying, initially it forces were balancing. What you're supposed to do is any torque that is changing, you have to include. But same thing when you do for the block mg is not changing. So when you write for the block, we don't write mg. But torque due to a rod, you will take. If you understood what I was saying. Think, try, I'll give another 2 minutes. It's a worthy question. It's a proper advanced one. Here, They also got the same simple answer. Let me show you. So first, let's displace this by small theta. So when you displace this by theta, so this spring here will stretch by L by 2 theta. This guy will go with alpha. So this point is accelerating with L alpha. And remember, this is connected to the block. That means the acceleration of the block is also L alpha. So every time this thing goes front and back, so the block and the topmost point of the rod will accelerate, move together. Is that clear, everyone? Great. So we got that. Now, if I write the forces, again, I'm exaggerating the figure here. Theta is not this big. So we have forces here, K into L by 2 theta, that is elongation. This is the tension, and this is mg. So initially, if you observe, initially torque due to mg is 0. So we are writing all the change in torques. After displacing, torque to mg is not 0. We have to include that. And if you look at the block FBD, we'll have tension and we'll have acceleration. So here we'll not write mg. Mg doesn't change. The mg of the block doesn't create any extra thing. So there's a change in tension. So T will be minus ma. Are you getting why I'm writing for the rod, but I'm not writing for the block? When you displace the block by x downward, did mg change before and after? It remains same. What changes? Only the tension. But when it displaced the rod by theta, the tension changed, spring force changed, and mg ka torque changed. Is that making sense? So you have to include all three of them. So what you need to see is every time after displacing, what are the things that are changing? You include them. So you have to, when you're doing angular thing, you have to check for torques, not forces. So now when you take torque about the hinge, and this is the alpha we have taken. So mg ka torque, mg into perpendicular distance will be how much? Mg, this is the perpendicular distance, that would be L by 2 sine theta. plus tension into L sine theta minus K into L theta by 2 into L by 2 cos theta. The spring force into the perpendicular distance. There, this is your torque equation. So this is equal to minus ml square by 3 alpha. Now for small angles, sine theta is theta and cos theta becomes 1. This is mgl by 2 theta. But what is tension here? Ma. That will be ml alpha L into theta KL square by 4 theta. Bring alpha to one side. Torque due to hinges is plus only. Why did I write minus? Then this thing comes this side. This guy would become, why is there a theta here? TL. No, I did a mistake here. This is not sine theta, this is cos theta. Now bring alphas to one side. That will be 4 ml square by 3 alpha. Mgl by 2 minus KL square by 4 theta. So we get alpha is equal to 3 by 4m L mg by 2 minus KL by 4 theta. You can just alternate them because you need a minus sign outside. KL by 4 minus mg by 2. Please check the steps. Once you got this, you're done. So you'll get time period T is equal to 2 pi root over 4 ml by 3 KL by 4 minus mg by 2. Now for this, the roots have to exist, right? Inside you can't have negative. So KL by 4 must satisfy that is greater than mg by 2. If this is not satisfied, then you'll get a time period is undefined. That means the system will be in unstable equilibrium. Meaning when you displace with theta mg so strong, the rod will continue to keep going down, isn't it? The rod will never come up. That is what Max is trying to tell you indirectly. So if KL by 4 is less than mg by 2, that means if mg starts dominating, right, time period is undefined. Meaning this guy will never come back when you displace it. If it never comes back, meaning it is unstable equilibrium. That would be a second question in this if it's a paragraph. Find the condition for the system to be in stable equilibrium. Tension, the torque equation should be the whole tension. Why? T is also the, do you think initially spring is in natural length? No, na? Initially spring is also stretched. So this tension in the block is balancing the spring ka force. So what we wrote is that only change in tension ka torque, change in spring ka torque, change in mg ka torque. So this is change in torques. We're not writing full torques. Have a look at these equations, everyone. It's a good one. Tension is equal to MA minus ML alpha. Check out each and every step. Ask me if you're confused. Clear? Next one. Clear, na, Vihan? Niharika, got this? Nikhil? Clear? Daksha? Abhinav? Clear? Ansh? Next one, everyone. Let's say we have a solid hemisphere. Bhasam and radius are. It's not slipping. Find time period for small oscillations. You're getting how will this oscillate? Meaning, if you're looking into my screen, right, it's like this. Ever seen a rocking chair? Rocking chair. That's how it oscillates. Meaning, after some time, this guy will become like this. Then it will become like this. So it is just like a rocking chair. Time period for small oscillations. There's no slipping on the floor. Just give it a try. Any answers? How do we start? So when you displace this, now again, I'm exaggerating the figure. Theta is very small. So if I take this point as A, then initially this was that central line. This was R. This was theta. So what are the forces? We have normal reaction. We have friction. Now mg will act somewhere here. Where will mg act? At center of mass, isn't it? So if we take torque over the bottommost point, the center of mass mg is actually creating the torque. And what is the distance of the center of mass? Solid hemisphere. 3r by 8. So from here, what is the perpendicular distance? 3r by 8 sine theta. So torque about A will be mg 3r by 8 sine theta. This is equal to minus Ia into alpha. Yeah, if I find Ia, my job is done. But understand, this thing is actually very small oscillation. Theta is very small. So if this was the center, A is almost this only. We can just ignore the distance there. We can almost say they're almost same. So we can take this as center of mass. This is O. This is A. We know IO is 2 by 5 mr square solid sphere, which is ICOM plus parallaxis theorem. This is 3r by 8 and this is 5r by 8. You want about IA? That is I center of mass plus m into 5r by 8 whole square. Subtract them. This guy will be how much? 9 minus 25, 16. 16 by 64 minus mr square by 4. 2 by 5 plus 1 by 4, 4 to 8, 8 plus 5, 13. 13 mr square by 20. So for small angle, this guy will become theta. 3 mgr by 8. Theta is equal to minus 13 mr square by 20 into alpha. 1 r will cancel. Alpha will be, this is 4 2s, that is 4 5s, minus 15 g by 26r. There, that's your time period. So the headache here is actually finding the mode of inertia. Read out some of the steps. Did you guys solve that question last time what we did? Jo rod wala and that thing, someone was asking also, how do we get alpha? Did anyone try this? Hi, again. Are you guys able to figure out that angle? So here, if you want this angle now, look at this thing. This was alpha. If you draw one more line like this, this line was alpha. No, see, if I draw one more line parallel like this line parallel to CD. So if that was alpha, this guy is also 90. Isn't this angle also alpha? This line are parallel. And both are making with this line and this line are parallel. So if this is alpha, so this is also alpha, no? So this line also will be alpha. So that means this angle will be 90 minus alpha. If that is 90 minus alpha, and I know this total angle is this, so this is again alpha. Then you will get it, I guess. क्लियर? तो ट्राई कर लेना वो, इट इज ऑल ज्योमेट्री देयर. नेक्स्ट वन. Suppose if you have a circular bowl here. Inside this, we kept a solid sphere. Mass is m and radius is small r. You displace this by small theta, and there's no slipping here. So how will this thing go when you leave it? It will roll like this now. This will be rolling on this thing. So it is rolling on a circular track. So this thing is going in a circle of radius r, and the whole thing is again a radius of capital R. Find time period for small theta.
अभी बनाइए तो
So we have a cylinder rolling inside another cylinder. The outer one is fixed though, capital R is fixed. Let's see. That might look right. No, that is, you didn't get capital R in the answer. Rehan, you didn't get small r in the answer. See, so here the catch is, see, this is the first thing you need to understand. You are displacing this theta, means you're interested in this alpha, not the alpha of the cylinder as a sphere. We have two different alphas here. Now, when you draw this solid sphere, if you look at the forces, we have friction, we have mg sine theta, we have mg cos theta, we have normal reaction, we also have a center of mass, and we also have alpha dash. This is the bottommost point. So if you take torque over the bottommost point, we will have mg sine theta into r is equal to minus ia alpha dash. This guy will be 7/5 mr square alpha dash. So from here we'll get a is equal to minus 5g/7 sine theta. So this is the acceleration of the center of mass as function of this. But remember, what you want to find is alpha of this thing, right? This line. So what you have is this. So this point here is going with a center of mass. And this is your alpha. This is your distance. So we are using A tangential is equal to R alpha. So here A tangential is a center of mass, which is minus 5g/7 sine theta, and R is the radius, which is R minus R. For small angle, sine theta becomes theta. So this is minus 5g/7 into R minus R into theta. Makes sense, everyone? So here we are dealing with two different alphas. Alpha dash of the cylinder, a sphere that I'm not interested. What I'm actually interested is this alpha. Because when you displace that by theta, you need to find that alpha in terms of this theta. Alpha dash has no role to play with that theta there. So you need to find the acceleration of center of mass of the solid sphere, and from there you need to get the angular acceleration, and then you're done. The time period will be 2 pi root over 7 into r minus small r by 5g. Check. Is this clear, everyone? Got this? Next one. So it's not tough in terms of solving, but yeah, there is a confusion like which alpha are you talking about? Next one. Let's look at this question. I'll just draw the diagram again. So this is the top view. We have a massless rod connected to a cylinder. So we have a rod here, connected here. This is a rod here, connected to a spring. This is K2. This is connected to another spring, K1. So basically the rod and the springs are not connected. They're just very side by side. So this is a hinge. Other than that, you have point P, and point Q is also hinge. Meaning, how will they rotate? If you try to rotate this system, the rods will become like this. Not like this, wait. And this is how it will be. You're getting it? This point and this point cannot move. They're hinged. So when you rotate, that is how that entire frame will rotate. So P and Q are hinges. This distance is R. I'm just redrawing the diagram. Same thing. This is 3R. This is R. This is also R. Rods are massless. Disc ka mass is M and radius is R. Now, if you rotate the disc by small angle and leave it, this will oscillate. Find time period for small oscillations. This is the top view. Check it out. Anyone confused with the diagram, please ask. How do we proceed? Start like this. Let's displace this by theta. Draw the picture first of all. Let theta be a little big for the picture purpose, and then later on we can say it is small and all. Just draw a picture where if I rotate this disk by theta, how will the picture look like? Start with that. Take a minute, then I'll show the picture. Let me show you. So initially, this was the picture. This was P and this was Q. Now, when you displace this by theta, what did you do? This point here will go down by r theta. This point here will go up by r theta. On top of it, this rod will become something like this. Again, it's not up to scale. This will become like this, where this angle will be theta and this will also be theta. And remember, this distance was 3r. That means, look at this thing here. So from the bottom, this thing has pushed up by 3r theta. Okay, smaller, Kepler, all are same. I'm just using them in the same way. Just put smaller. This was 3r, so this thing is also pushing from 3r theta. That means the spring on the right hand side, right? It got compressed from both the sides. This is a compression because the rod moved. The upper ka r theta is because the disk moved. So the right hand spring got compressed by 4r theta. Is the picture clear area? And this upper ka spring got compressed by only r theta. Now what? Now draw an FBD. Now find torque is equal to I alpha, get alpha in terms of theta, and job's done. This is the first thing. This is all based on constant kind of thing. So if you displace the disk by theta, your job is always to figure out what are the compressions and elongations. Making sense? Na? Suppose if the rod was not there, won't the spring only compress r theta? K2 ka spring. And because the rod also moved, it pushed it from down and the disk pushed it from top. So the whole thing got compressed by 4r theta. So if I draw this thing, if you look at the forces, so from this side, you're getting K2 into 4r theta. We are also getting tension here. We are also getting this is pushing with K1 r theta. There. This is alpha. Now the headache is to find tension. So torque about the center will be T into R plus K1 R theta into R plus K2 4R theta into R is equal to minus I centromos alpha. If I can find T, my job is done. How will you find T? You can read the question for any hints. In case you didn't figure out, this is the hint. The rods are massless. So what? Try. I'll give you a minute, figure it out. See, the catches. What are the catches of the massless rod? If I draw this FBD again for this guy, look at how the rod is. So again, like I said, I'm exaggerating the figure here. It's almost horizontal only. This is the axis P and Q. So it is about this, it is rotating. So here we'll have tension like this. Here the spring force is pushing it. This is almost perpendicular, which is K2 into 4R theta. You're getting it. Technically, now picture should look like this only, right? Almost it is still horizontal only. I'm just showing it for this effect. This is radius R and this is radius 3R. So if you take torque about PQ, this is only for the rod. So there are only two forces fighting, which is T into R minus K2 into 4R theta into 3R is equal to I of the rod into alpha. But rod is massless. That is the catch. If you have a massless rod, the tension will be same everywhere. So from here we can get tension is equal to 12 K2 R theta. Clear everyone? K2, 12 K2, 1 R will cancel, K2 R theta. That's how you get the tension, taking the rod ka steady state. T is perpendicular because, like I said, look at the picture here. Is this spring force perpendicular to the rod? Theta is small, na? It is still perpendicular. Are you getting it? The picture would look like this, right, Purvaja? You getting it? Because theta is small, I have exaggerated the figure for you to see the rotation. If you rotate with theta, angle kitna hoga? This will be almost 90 minus theta, where theta tends to 0. It is almost 90. Is that making sense? I know the picture is pretty deceptive. Getting it? Theta is actually very small. So spring force is almost perpendicular. Here I exaggerated the figure. And then you're done. Substitute here. So this guy will be 12 K2 R theta square plus K1 R square theta plus 4 K2 R square theta. Disk will be MR square by 2 alpha. You're done. So how much is this? 16 K2 plus K1 into 2 by M theta. That's your omega. You get the answer from there. Clear everyone. So the two spring forces and the rod cut tension also had to include. It's a little tougher one, but there. Clear with this? Definitely try this today. Whatever we did, right? If you see all our little on a advanced level problems only, should definitely try these things. Okay, take a break. Come back by 7:03. We'll continue from here. Yeah, the tension will be along. No, what is this thing? This is this thing, na? We are talking about this force connected here, isn't it? When you pull this up, what will happen? This rod is generating a tension, right? That's a tangential force. Chalo, we'll think this way. If according to you, na, if you want tension, right? A काम करो. Let this be Ty, let this be Tx. Happy? Tx is passing through the hinge, so there'll be no torque. So this is actually only the Ty ka component. And this will also write as Ty. Fair enough? Hmm. Okay, come back in 10 minutes. Yeah, comes on everyone. Let's see one more easy one. So let's say we have a disk here, we got a spring here, we attach a block M here. This is a disk of mass and radius r, and there is no slipping. So be careful. This is not the same question as what you have done before. In the previous thing, when we did this, the disk was smooth. So what is the difference in both the things? Look at the difference. This is how it would look. If you look at my screen, right? In the first case, when it was smooth, this was what is happening. This was the string. It was simply sliding. You're getting, and the pulley was fixed. The pulley was smooth, no? The pulley never rotated before. The string simply went upper, just slipped. But now what will happen? The pulley which is there, the pulley also will rotate. So now the motion will look like this. The pulley is rotating, block is coming down. You're getting the difference? That K equivalent, which I taught you, if you remember, you can't use that. This question. This is a smooth massless pulley. The pulley never, rotated. The pulley was just there. But now in this problem, even the pulley will rotate. So here the pulley rotates. So that is the thing when you say no slipping. Basically, the tension on both the sides won't be same. Find time period for small oscillations. If you guys remember, in rotation, we did the net pulling force method, yeah, the net torque method. How do we do that? We attach the block at the point where the string is connected. Try that. That will make your life easy. You will get the answer in pretty fast steps. Try. Take a minute. Let's see. These kind of questions, right? What we do, since the block and the pulley are going with, that same thing, they're going together. Now, my question is this. Do you think the answer will depend on this length of the string here? Do you think the answer will depend on that length of the string there? No, right? So what if I make the tension that length of the string 0? So attach the block. So if that string is not going to matter, then let's remove it, right? Attach the block at the point where string meets the pulley, because the string is anyway massless. Then your diagram will become like one spring here, mass m here, and the disk is m and r. Now displace this by theta. Then this point will go up by r theta. Therefore, the spring car tension will be, so now if you look at the FBD, we will get this will be K into r theta. Remember, this is the change in spring force. Spring is already elongated by some amount due to the mg's there. This is the change in spring force. We will not write mg because mg ka torque didn't change. Initially, mg ka torque was balancing spring ka torque, and those will get cancelled. And this guy was alpha. That's it. There's only one force. So K into r theta into r, that is the torque about the center. Here the difference will come, is equal to minus I of the system into alpha. Now, what is your system? Your system is a disk plus a particle. So K r square theta is equal to disk will be mr square by 2. And the particle which you attached here will be mr square. This is for the mass. You will get alpha is equal to minus 2k by 3m. Done. Check.
Sir.
Hmm.
So could you explain why MG top didn't change?
So you think it changed?
Like, sir, it went up by an angle. So, like,
So how much is that? Tell na. That means you think it changed, right? So how much did it change?
okay.
Initially, it is like this. कितना था torque?
Hmm.
कितना था? हूँ क्या? Follow.
MGR.
Now if you displace with theta, this small angle, do you think the perpendicular distance changed?
Okay, right. Perpendicular distance. Got it.
Theta is same. The game is still the same. Theta is small. So कितना होगा? Perpendicular distance r cos theta होगा. Theta is almost 0, so it is still r only. So that didn't change. Is this clear, everyone? So if you see, this is a bit about angular SHM. So where things were rotating and stuff. Now all these questions, right, we did using forces and torques, but there's another way to do this using energy method. Now this method I don't like much, right? But there are one or two models where you can't solve using force method and torque method. It doesn't work. There are a few cases which we will see, one or two cases. So there is another way to solve all these problems. So we call this thing energy method. So let me show you how it goes. The reason I don't like is because it involves additional steps. You will see. But at a mains level, you can do with just in force and torque. Energy method, if at all they ask you, it will be an advanced question. So the concept is pretty simple. In an SHM, total energy must remain constant. The total energy of SHM is constant. So consider we have a spring and block. So step one, choose your system and displace it from mean position by x. And after displacing by x, let the velocity be v. Acceleration be a. Step 2, calculate total energy. Step 3, differentiate with respect to time. Now, because the total energy is constant, the total energy term will become 0. And then you will get something. You'll get acceleration from there. Compare with a is equal to minus omega square x. So let me show you one or two examples. So let's look at this case. So initially the block is at the mean position. Step 1, displace it by x from the mean position. You displaced it by x. Let the velocity be v. Let the acceleration be a. Total energy. It has two energies, spring energy plus kinetic energy. The total energy will be half mv square plus half kx square. Differentiate with respect to time. The left hand term will be 0. This guy will become half m 2v dv by dt plus half k 2x dx by dt. 2 goes off. This will be 0. This will be mv dv by dt is acceleration. This is kx dx by dt is velocity. V ka term goes off. You'll get ma is equal to minus kx. A is equal to minus k by mx. Compare with this thing, you'll get the time period. Make sense? How did we do this question normally? Displace it by x. What is the force? Kx is equal to ma. Done, na? But you saw the steps, right? Energy karo, wo karo, ye karo, put all that. It becomes messy that way. Becomes lengthy. Got the thing? Let me show you one more example. Let's say we have this cylinder here. I'll just take two springs. Let's say this is K1. Let's say this is K2. Let's say it is not slipping. Let's take it as solid cylinder. Mass m and radius r. Again, same story. Displace the cylinder by x. If I displace this by x, this upper spring will go by 2x. This spring will stretch by x. Let the velocity be v. Let it rotate with omega. Let the acceleration be e. Let it rotate with alpha. We know a is equal to r alpha, v is equal to r omega. No slipping condition. Now, what is the total energy? Now, total energy will be for the cylinder half mv square plus half I omega square. You have to take the total kinetic energy. So there's a rotational kinetic energy also included now. Plus half k1 x square plus half k2 2x ka whole square. Check out the terms. So two spring energies, and then we have to get one rotational kinetic energy, one translation kinetic energy. Once we get this, now differentiate. The left hand will be 0. This guy will become mv dv by dt acceleration. I'm skipping steps now. Omega square ka differential 2 omega. So that will be I omega d omega by dt is alpha. This is k1x dx by dt is velocity. That would be 4, na? 2 k2 4 k2 x v. And what is I? I is nothing but mr square by 2. So one r will go with omega, one r will go with alpha. Then you get 0 is equal to mva plus mva by 2 plus k1xv plus 4k2xv. V goes off everywhere. we get 3 ma by 2 is equal to minus k1 plus 4k2x. There, you are the answer. Minus 2 by 3 m plus k1 plus 4k2x. You get the answers. This is a way to do. And this is the reason I don't like. You have to include that energy, this energy. And the worst part, you know what? If the springs are already compressed, you have to include that initial compression also. Because the energy will be half k x plus y whole square. Na? Now in our all the methods, what we did, we ignored the initial conditions. But in energy terms, when you say spring energy, you can't write half k x square. You have to write half k total elongation square. So it means you need to find the initial compressions if they exist. So this becomes really lengthy. But like I said, there are a few problems you can't do with the force method. Let me show you one. But clear with the method? Let's say we have a spring here with a block. If the spring has mass, if you take problems with mass springs, so we have a spring with a mass m. The mass of the block is much greater than m, but the spring does have some mass. So here, one thing that we can assume the velocity in the spring is varies linearly. I'll tell you what it means. They will generally mention. If they don't mention, you have to assume. There's no other way to do this. But the problem with this thing, in the force method, tell me one thing: when the spring is stretching, do you think every point is going with same velocity? Look at this point here. This point connected to the wall. What is the velocity? Zero. वो कभी move नहीं करेगा. This point which is connected to the wall, what is the velocity? V. That means the spring is not stretching uniformly, right? If the spring is not stretching uniformly, do you think the center mass will be always in the center? So the spring ka center mass is also moving. So when you say F is equal to ma, you're taking A of what exactly? You're taking acceleration of the block or center of mass or force. It becomes a mess. Matlab, if you try to do force method, you won't understand where to apply exactly what. So now for this spring, when you say velocity varies linearly, this point has velocity 0. This point is going with v. So at a distance y from here, if you take a small slice, this point will go with velocity vy, or let's call it v dash. So v dash will be velocity by length L into y. It varies linearly. So every point on the spring will have different velocity. It varies linearly. So that is an assumption you need. Now you can't use force method. So can you solve this question using energy method? Find time period for small oscillations. We're assuming the mass of the spring is very small, so this approximation works. If the mass is too big, then the center mass will get affected too much, and then even energy method also will start failing. Meaning, just to give an idea, what is the total energy now? Total energy will be half mv square, energy of the block, half kx square, energy in the spring, plus kinetic energy of the spring. अभी ये भी extra term आएगा. This we don't know. That was a catch in the question. So if you can find kinetic energy of the spring, my job is done. And then the story is same: differentiate, equate, and get it. Try. I gave you velocity for each point on the spring. So every point will have a different kinetic energy. You have to integrate. Let's see. So at a distance x, distance y, take a small slice dy. So mass of this small piece will be total mass of the spring by total length of the spring into dy. And this thing has velocity v dash, which is v by L into y. It's a linearly varying velocity. Therefore, the kinetic energy of the spring will be summation of half dm v dash square. This will go from 0 to L. Half dm will be m by L dy, that will be v square y square by L square. This will be m by 2L cube, and that will be y cube by thing, that will be L cube by 3. You get mv square by 6. There. So the kinetic energy of the spring is mv square by 6. Therefore, total energy will be, block will be half mv square. Spring will be half kx square. Spring kinetic energy is mv square by 6. Now the story is the same, differentiate. This will be 0. This will be mv dv by dt acceleration. This will be kx dx by dt velocity. This will be mv by 3 acceleration. V goes off. We get acceleration is equal to minus kx by. You can actually kind of remember the result. The whole spring will behave as if it is an additional mass of m by 3. These are the kind of questions where force and torque, force methods don't work. At least I couldn't figure out so far. So energy method is the way. There are still a few more variations, but we'll see them later on. But I hope you got the method. So know this thing. It's even though it is lengthy and all, it has its own uses. Especially advanced perspective, we need it. Clear, everyone? The next thing is a torsional pendulum. We just have a bit of a theory. So this is a main part of it, like, angular, linear SHM and different systems, like, thermodynamics, fluid mechanics. Later on, when we do gravitational electrostatics, even then SHM will, so SHM will keep popping up in every chapter now. Turning the page, any doubts so far? Clear, na, Ansh? Arnav? Parth? Ojas? Sharman? Clear? Next thing is the torsional pendulum. Look at the word torso. So torso is like your hipka part. If you're sitting straight, right? If you can, if you keep your legs forward and try to turn your head backward, can you see what happens? If you try to do 180 degrees with your head, keeping your legs forward, your hip will twist, isn't it? Your body will try to come back to the front again. So that is basically torsional meaning twisting. Did you ever do this thing when you're a kid? Meaning you must have done now also. I used to do this when I was a kid. We have a swing. We sit in the swing, and instead of swinging, right, you try to rotate the swing. And then you leave it. What will happen? You'll rotate front, left, right like this. Ever did that? So something like that. It's like a twisting thing. So when a wire or a rod is twisted, we have done this in elasticity, if you remember. Rigidity modulus maybe did this thing. I told you it will come again. When a wire is twisted, it generates an internal restoring forces, or you can say it generates a twisting or a torsional torque. So torsional torque is a more technical name. So if you have a disc, if you have a wire, so we define K is called torsional constant. Questions are straightforward on this. So if this was point O and this was A, and now someone tries to twist this by theta, this wire will get twisted. It's like someone is catching your hand and twisting it. You must have done to your friend, or someone must have done to you. Or when you're pinching your sister or brother, your pinching is actually twisting only. You're generating torsional torque. So this wire gets twisted. So we get the torque is proportional to minus theta. This is your one sec. This is your torsional torque. This is your twisting angle. Angle twisted. So we get torque is equal to minus k theta. This is equal to I alpha. Then as usual, your SHM will come and say this is your SHM there. That's your omega square. Therefore, the time period is given by 2 pi root over I by k. K is your torsional constant. So K tells you how difficult it is to twist a wire or a cylinder. Great. So how will these things be? Equations will be like this. So if you have taken this disk, they will give you the kk value. The moment of inertia will be mr square by 2. Therefore, the time period will be 2 pi root over mr square by 2k. Or if they give you a rod and they put a wire, so there is nothing there. You should just know the moment of inertia, ml square by 12. So if you twist this rod and leave it, you'll get time period 2 pi root over ml square by 12k. बस इतना है the torsional constant. So they will give you the k value. You need to figure out the I value, substitute, and you're done. At a mains level, they will ask you only till here. They can't go beyond this. If they want to go until advanced, then you have to bring the elasticity question in this. Let me show you that one. Clear with this? So end of the story is the same thing. This is a twisting torque. So this is the result which you should know. This is the time period for torsional pendulums. Now that one was for cylinders or for cylindrical wires. If you have a cylinder, fixed, length L, and radius R. If you twist the cylinder by theta, then we know that result, the torsional torque. is given by pi eta r power 4 by 2L into theta. So there, this is your torsional constant. So it depends on the radius, it depends on the length, and depends on the rigidity modulus. So where did this come from? Elasticity. This question, page 50. Remember the derivation? We use rigidity modulus to derive this thing. So definitely check it out. I will write it down there. You can refer this. So refer elasticity, page 50. So that means if you take two cylinders, if they want to ask in advance, they will mix up something like this. Then they can ask you, find the torque required to twist it, or find the torsional constant and find the time period. So if you take two cylinders of same length, but if this is radius r and let's say this is 3r, you know the meaning of this? This guy is 81 times more difficult to twist, 3 power 4. Means if you apply same torque, that will rotate only theta by 81. Clear with that? So K simply tells you how difficult it is to twist a body. So thicker the body, the more difficult to twist. Longer the body, more easy to twist. Remember this thing? Elasticity में क्या था ये? That's it. That is about torsional pendulum. It's a small concept there. Not much questions also. I mean, क्या questions पूछेंगे ना? I'll give you the shape. You have to find I and dump it there. So there's nothing you can really push in that. Then we have something called damped oscillations. Now, damped oscillations is removed from the mains portion from this year. So technically it is not there, but advance में अभी भी है. Advance में it is written. So next year, until we get the new advance का portion, we don't know whether it is there or not for you. That is one. Second thing, HSC में they do have a little theory on it. Bits में they might still have it. So we are clueless what it is, but let's do it. It is not much. There are two to three formulas you need to remember the main ones. I'll just finish all the theory part, and then if it is there for advance, then again I'll revise in the end when we do the revision, and I'll teach you again one more time. I will teach you at a much higher level then, but for now at least you should know the basics. The next one is a damped oscillation. So technically with whatever we did till now, you'll be able to handle everything. So in damped oscillations, if a system has an air resistance, or some kind of resistive force acts on the body, you won't get this regular SHMs, things get messed up. So even in that, we study a very special case. So let's say we have a viscous force, or let's say F resistance. Don't worry about too much about the math part. So just listen. BV. I'll tell you what are the main results to remember. We study only for linear variation because you can even have BV square, you can have BV or 1.5 or anything. But we will keep our study only to linear variation. So even in whatever used to be there, it is only linear variation. This B is called damping constant. Basically, B tells you how high the resistance is. If B ka value is very large, for example, if a ball is going in honey, right, or if a ball is going in water, honey ka damping constant is much higher. It is more viscous and it is more difficult to walk in honey that way. Or same thing when you're walking in air normally on the ground, or when you're walking inside the water, isn't water more difficult? So water has more damping coefficient. So higher the B, more the resistance. V is the velocity. So just to show you how it would look, this is the picture they use in HSA. So I'll use the same thing. So we have a spring and block here, M. And then you have some kind of a small platform here, which is placed in a liquid. So the block is not inside the liquid. The block is simply going. Damping coefficient depends on the nature of the material and the shape of the body. That has nothing to do with velocity. This is a viscous liquid. So that thin platform which is there, that is actually getting that liquid resistance. So now if you draw the FBD of these forces, let's say if it is going down with x and let the velocity be v and let the acceleration be a, and then we will have the F resistance, which is PV. The minus indicates opposite to velocity, so I'm keeping it up. This is Kx. We will not write mg because mg doesn't change. So we get a BV plus Kx is equal to mass into acceleration. So if you bring it this side, this will be m into acceleration. This can be written as m into d square x by dt square plus b into dx by dt plus k into x is equal to 0. This is a differential equation. So if you put b is equal to 0, it will become your regular SHM ka problem. If b is not 0, this is something else. So for this, you will learn in max, we have a chapter called differential equations. So for this thing, the solution comes out like this. So m into d square x by dt square plus b into, this is not important. You need not know this stuff, but I didn't want to give the result directly. Meaning even that result also won't come that neatly. We have to derive one small thing. I'll show you that. So general solution for this, for differential equations, this is how they solve. We put x is equal to a into e power alpha t. Why is that? Max teacher will explain. I'll not get into that. This will be a into alpha e power alpha t. Double differential will be a into alpha square e power alpha t. So when you substitute here, you get ma alpha square e power alpha t, ba alpha e power alpha t, ka e power alpha t. So the e power alpha t has an advantage. When you differentiate, it remains same, so it goes off. So you end up with m alpha square plus b alpha plus k. So for this, when you write the quadratic equation, we get minus b plus or minus root over b square minus 4mk by 2m. And we know x is equal to a into e power alpha t. So if you substitute alpha, you get solutions. This is how the max ka story goes on. Getting it? Now, in this, look at this thing. So we are interested in this part actually. Again, I'm saying don't worry about all this stuff. You don't need all this math, this much math part. When it comes again, advanced way, then I'll tell you in another way. We can actually do this using AC circuits. That becomes quite easy. But for now, we don't know AC, so I can't teach you. So why do I need this? Just to show you this part. So we have three cases now. Case one, so for whatever solution that I got, if the roots are real, means if b square is greater than 4mk, this is the real root. This is called overdamping. Like this, they can ask you questions. What is the condition for overdamping? What do you mean by overdamping? Look at the word. Meaning there is so much resistance, the system doesn't oscillate only. For example, did you ever see this kind of door in the offices? You have a box kind of thing here and there's a rod like this. Kabhi dekha? And when you open the door and close it, the door aaram se closes. Seen that kind of door? So this is a system of overdamping. Matlab, when you open the door and leave it, technically, think about it. If you keep a spring here, open the door and leave it, what should happen? The door should oscillate, right? That doesn't happen. So basically the thing is, this thing has so much resistance, the door simply just closes and stops. There will be no oscillations. This is called overdamping basically. So there will be no oscillations in the system. That is, when you stretch the system and leave it, it comes back to mean and stop. It won't oscillate, it will just come back to mean and stop. So tell me one thing, when you are going on a vehicle, you have shock absorbers, no? Should the shock absorbers be overdamped or not overdamped? Think about it. When you're going over that speed breakers, you want the vibrations to come to your body or don't want the vibrations to come to your body? We don't want, right? If it is not overdamped, what will happen? Every time you go over a bumper, you will just keep on oscillating like this for few seconds. You won't get a comfortable ride. So it should be overdamped. So these are some examples of that. So a spring door, right? When opened and released, it comes back to initial position. Shock absorbers in vehicle are overdamped. So these are some examples of overdamping. That one. Case 2, what if the roots are real? B square is equal to 4mk. This is called critically damped. So technically, there is no difference between this and overdamping. The only difference is there will be no oscillations. The only difference would be this. When you open the door and leave it, the body reaches the mean position in the shortest time. So here also will not oscillate, but it will reach the mean position in the shortest time. Just mean position in least time. Making sense? So meaning if you make a spring door, right, with a over damping and a critically damped, and if you open both the doors and leave them, this critically damped wala will come to the mean position and stop. That will happen faster than the over damped one. So these two cases, right? But it is very difficult to design a critically damped, na? थोड़ा mass change हो गया, थोड़ा K का change हो गया, कुछ भी हो गया, values will get messed up. Case 3 is the one which we are interested in. This also we don't have big results. So if B square is less than 4mk, we will get imaginary roots. These are the main things you need to remember. This is there in HSC also. Case 3. So this is underdamped. So for this central equation, B square dx by dt square plus B into dx by dt plus kx is equal to 0. For this, the solution will be, because the roots are imaginary, a into e power minus bt by 2m. We will not go into how we got this, sine omega d dash plus phi. This looks like an SHM equation, but if you look at this amplitude part, this is not constant. The amplitude is decreasing with time. The amplitude here is a into e power minus bt by 2m. If you try to plot this graph, a normal sine graph will look like a sine wave. So, but this guy will be a sine wave with decreasing amplitude. You're getting it? The amplitude will keep on dropping. This omega dash is given by root over k by m minus b square by 4m square. Time period is given by 2 pi by omega dash. Plus, these are the results which you should know. Can you just note down these results? Especially this one we'll need. You can just put it on. Actually, I'll write it down, but just have a look at this. That's it. This page is the most important one. All questions, all numericals are based on this only so far. If at all they ask you, they'll just ask you what is the condition for over damping. You have to write b square greater than 4mk. Critically damped, b square is equal to 4mk. Under damped, b square is less than 4mk. Just you should know that much. Yeah. Let me show you the kind of question they asked. So amplitude of a damped oscillation. You will need this for HSC. This is HSC. This is an example question. A is given by A naught into e power minus bt by 2m. Find the time when the amplitude becomes half and find the time when the energy becomes half. Plus, these are the only two numericals you have. Meaning I can change when amplitude becomes 1/4, amplitude becomes 1/3 or something like that. Don't worry about that. There are roots for that. But differential equations don't behave like regular quadratic equations. Find the time when the amplitude becomes half, find the time when the energy becomes half. There. Let's finish off with this. It is just math. I already gave the equation. Chemistry, did you study chemical kinetics? Is it done? If you have done, there is a first order reaction. If you remember, n is equal to n naught e power minus lambda t. It looks exactly like that. There is something called half-life. It works exactly like that. It works if you have done chemical kinetics. Yeah. First one simply half amplitude, so a naught by 2 is equal to a naught e power minus pt by 2m. Put ln on both sides. टू एम by b ln 2. बस इतना ही था. What about energy? Half time for energy. What do you mean by that? Find the time when energy becomes half. What is the energy of an SHM? Half m omega square a square. So if energy becomes half, amplitude becomes 1 by root 2 times. Nah, it doesn't become half. So a naught by root 2 is equal to a naught into e power minus bt by 2m. Same story. Put ln on both sides. That will be m by b ln 2. Clear? That's it. These are the numericals you have in damped oscillations. So what are all the questions I can ask you? One thing they'll ask you, what is the condition for overdamping, underdamping, critically damped? One. Find the equation of SHM, equation of this damping, x is equal to this. What is the omega dash? What is the time period? And what is the amplitude? These are the 3-4 questions they can ask you. They removed it from the mains, but this year they did ask in one of the paper. But luckily they gave bonus, so it worked out. Is this clear, everyone? So there. So with that, we are done with the chapter SHM. So next class, when we catch up on Tuesday, we'll start off with electrostatics. So first we will do electrostatics, and then is electrostatics done for most of you, right? Is there anyone whose electrostatics is not done or not even started? They didn't even start? Gravitation started. Gravity is also not started. What are these people teaching? रे मतलब क्या chapter हो रहा है exactly?